Welcome to Tailored Materials and Surfaces. Today we're going to talk mostly about the second part, the surfaces, or I am, because you can't reply very easily on the other side of the camera. So first of all, we're going to investigate the surfaces, and then we're going to look at the tailored materials part afterwards. So many of you will be familiar with the crystal structure. This would be a simple two-dimensional crystal, obviously not realistic, but it's a drawing, it's a diagram. So we would think of a material as having some kind of crystal structure. That would be most metals, many inorganic materials, even some organic materials will form a crystal, and there will be bonds between the different substances, either ionic bonds, covalent bonds, or in between, and metallic bonds as well, of course. And we would imagine our bulk material as being an infinite crystal with continuing on forever. Whoops. If we think of it as a surface, however, we have to break this somewhere, which is what we'll do now. So now I've removed not only the text, but I've also removed the top layer of atoms, and now we have a problem. The problem is that there are some extra bonds left over, and they're doing nothing. In chemistry, we like to think of them as dangling bonds, so bonds that go to nowhere. In other subjects, they're just unsatisfied bonding potential. They are atoms that don't have their full component of surrounding other atoms, and obviously they can't just hang around like that. That's not realistic, so at the surface, something new is likely to happen. So let's look at what would happen if there was nothing else around and they were just free to react with nothing. So now I've drawn it in chemistry mode. If we have a dangling bond, if we cut a bond in half, each of these atoms will end up with one of the electrons that used to be in the bond if it was a covalent bond, or if it was a metallic bond, it would be part of the electron density. And now they can do a new thing. So they could now react with each other. That's one electron coming in, another electron coming in to form a new bond. So every other atom on this surface would then have a double bond, single bond, double bond, single bond. And as a double bond is way more strong than a single bond, although not quite twice, these should be closer together than these. So now we need to rearrange our atoms in our surface accordingly. So now what we've got is a shorter pair, and then a longer gap, and then a shorter one, and then a longer one. And that will be what our surface would look like. Obviously it's a two-dimensional surface, so it's not like this one-dimensional surface that we've got here. So if we take a two-dimensional surface, we will see rows of atoms that are closer together and rows of atoms that are slightly further apart. And that is exactly what we see on some crystals, such as silicon. So if we take a silicon and we take specific surfaces, cuts of the silicon, the atoms in the surface will rearrange themselves to form lines of pairs of atoms that are slightly closer to each other. But that is a problem, because now these ones underneath are under strain, and they are also going to follow slightly and move slightly out of line from where they were before. And that will move the ones below. And so there will be a disturbance in the atom's position down to fairly far down below the surface. But we have managed to get rid of some of the extra energy on the surface, which would otherwise be in open bonds that were ready to react with anything. So now if we add another layer to our material, somehow, then it will have to add to this already disturbed layer, and then the layer will have to reorganize back to the original crystal structure, and this will have to be the surface. So if we add a layer to the surface, or we take a layer away, it causes the atoms to reorganize so that the ones at the surface have this special structure, and the ones below the surface have their normal crystal structure. And between the first 5 atoms, so I haven't actually drawn enough to get to bulk here, but between the surface and the whole crystal, there's a little bit of distorted material, which is why very small particles behave very differently to bulk material. This happens if we add material, but it also happens if we take material off. So if we cut it, then both sides have to reorganize. And remembering this is just a special case where they form pairs, it's quite common, but it's not the only thing that can happen. It depends on what's left over. In this case, there was a covalent bond left over, so in silicon, it's quite common for this to happen. In metals, it's not so common because they don't have a bond, they have a metallic bond that's left over, and so it does a different thing. But typically, the surface has a different type of bonding than the bulk of the material. Right, and obviously it can follow through and zip through depending on whether we add new material or whether we take some away and how we do that. So if we add a new badly drawn layer of some other substance, this is a different crystal, it has a different crystal structure. As you can see, it's triangular instead of square, it's two-dimensional, but the point still carries. If we take this extra material and we're going to bond it to here, then we have new problems. First of all, the length of the bond doesn't match, and second of all, the crystal structure doesn't match. So in this case, it doesn't matter in 2 dimensions, it's only going to be due to the length of the bond and the size of the atoms and what kind of bonding they can do. But if we have 2 dimensions, which is a typical surface, then it may not match in the other direction. They may form triangles and the other ones form squares, and that becomes very difficult or impossible to match, and so something new has to happen. The new surface has to distort to fit on the old surface has to distort to fit on the new surface. This type of rearrangement that it had beforehand will go away and be replaced by a different type of rearrangement so that the 2 materials can match to each other, but it will mean that there's a lot of stress between these 2 materials and the bonding between them won't be great if the match isn't very good. The other possibility is that the new layer of something new, so these red atoms on the surface, they close the surface off, they fit better to the blue material than the blue material does to itself. So in this case, they've finished the top, so they've removed some of that problem that we had, the excess strain, the strain of distorting this lattice here, the extra double bonds that wouldn't normally be in the bulk material. We've got rid of it by adding a layer of these red atoms to the top, which has now closed the surface. There are no extra bonds left over, dangling bonds as we mentioned before, and that has made the rest of the lattice be able to relax, which has got all of the strain energy out of these other layers down below. So that's one way where a single layer of a new material on old material can actually be very easy to put on because it reduces the strain, so we get all of this energy back. And if we think of it as a Gibbs free energy question, the global Gibbs free energy is not only this bonding energy here, and not only the loss of entropy because we've added some atoms that were free and now they're not free, but it's also the gain in energy from the strain, from leaving the strain in all of the other bonds down to maybe 5 layers down from the surface, obviously getting less and less as we go down because the strain is less and less, it's worse at the surface. So we can gain quite a lot of energy back, and this is interesting if we have some combinations of materials, because then the first layer that we put on is actually very easy to put on. It's easier to put on than adding the next layer, because then we have to do something. We've got no bonds going up here now. And so we're going to have to rearrange these in order to be able to bond our next material on, because as you remember, it was a triangular lattice of red things. I've made them smaller to fit better, but it was a triangular lattice of red atoms, and now it's turned into a square one, so now there's got to be some kind of change in structure between here and the bulk red material, which is triangular. So that will be then harder to deposit. So going back to our single simple surface, it's not very simple because it's got a rearranged top layer, But if we go back to that and we want to add a layer of new material, of our blue material, then we have to also think about how it's going to arrive. So the first one that comes along has got a problem because there aren't any bonds left over. They've all reacted to form these double bonds. So the first one will be here, for example. Got to put it somewhere. It will take this double bond, but then that's going to generate a problem because this one is now free, and this one here has other bonds that are still open. So however we attach this, it's either in solution, so we're either doing it by electrochemistry, or crystallization from solution if it's an ionic crystal, or if it's a metal, for example, we could be doing this by evaporation. This atom has got to come along and attach, and because it's got no friends, it's got nobody beside it, it's got nobody on top of it, it's got a very high amount of energy. If I now want to add another one to it, I could put it here, but it's a lot better, lower in energy, to put it right next to the first one, because then it can bond to it. It can form actually more than one bond to it, so it could form two bonds like it was in the original surface, and that is lower in energy. That leaves not so much left over, so we've now got 1, 2, 3, 4, so now we've only got 2 bonds left over, and they can bond down to these, which are now open. So they would then be doing something like this. It's still not great, but it's better than nothing, and then the next one that comes along can go on here, which causes new things to happen. So we can gradually fill up another layer. If we do that in 2 dimensions, so if we look from the top, this is the surface of our, let's draw it as a cross hatch pattern. This is the surface of our crystal below, and we're going to add new ones. I'll add new ones in different color because it's easier. Whoops, I've not given myself very much space here because of the way the camera fits in. So if I put one on here, the next one will tend to attach near to it, and then the next one will attach near to that. And as we go along, we're not trying to, but we automatically build what's called an island on the top. So we're making a new layer that grows out from an island. This is called island growth. It's a very common type of growth in materials if they're allowed to minimize their energy in between. So if these things coming along don't have so much energy, they just go somewhere. If they're allowed to move around on the surface, they can attach to the edge of this island, and it will grow until it's formed a whole new layer, and then the layer is clean and finished again, and then it's harder to start again. So we will see, if we measure this, that it will be easy to fill up the island until we get full, and then when we filled it, it will be more difficult to put the next one on. So if we're doing it by electrochemistry, we're going to have to increase the voltage to get the next layer to start, and then we can reduce it again and it will fill up, and then it will stop, and we'll have to increase it again, pulse it up a little bit to get a new one, a little few atoms to form like this, and then it will grow again. While we're here on this type of diagram, if we put a different material on top of this, there is no guarantee that it will sit on the top of an atom. That's where the normal crystal would go, but there's a bigger hole down here. So if it's a bigger atom, it will tend to sit lower, and if it's got more bonds, it can bond to more atoms that way, and so it will tend to sit in between. And it depends how big it is, so maybe let's have an even bigger one. We have an even bigger one. The next one can't go on any of these spots because it's too close, and so the next one would have to go maybe over here, which gives us a different crystal structure for this material. Let's have a triangular one, because why not? So we've got a new material on the surface, and it's got a different crystal structure to the underlying material, and it might be different also to what this would like to have, because it's dictated by the underlying blue material. So only this layer will have this particular crystal structure, and we can investigate this in various ways. That's our iron, and on the surface of the iron we would expect to have something else because the iron is in contact with the air. So outside here we've got air, and air contains some things that are going to react with the iron, which is mostly oxygen and water and stuff from my body, which I would usually, if it was like an interactive session, I would make you have to think of, but that would be things like fatty acids, acid, and bad breath, which would be sulfur compounds, thiols and things, sulfur compounds, organics. So organic sulfur, whoops, yeah, you can see that. Organosulfur, oxygen, water, fatty acids, those are going to interact with our iron. So even if we were able to make it completely new without anything on it, it would be reacting with the environment. So what's going to happen is going to grow some iron oxide on the surface. Let's just have one dimension here, so don't worry about what's happening in this direction and this direction. Obviously the same thing, or maybe it's more iron. So now we have a connection to a previous topic. So our previous topic would be corrosion, and if we're going to corrode this iron, there would be a change in the electrochemical potential between the iron, which is at the electrochemical potential of iron turning into iron 2+, because it's already iron 0. And on the outside, we've got the electrochemical potential of the oxygen. And so there's got to be some kind of way of getting from one to the other, and that's this oxide layer, which in iron is quite complicated because at each energy, at each potential, we have a different compound. So close to the surface we will have iron 2 iron 3 oxide, which is magnetite, so it's Fe3O4, let me see, yep, Fe3O4. So this has a mixture of iron 2 and iron 3 in it, and on the surface we've got more normal rust, so Fe2O3, so iron 3 oxide. That would be our normal rust, and on the surface of that we would normally have some kind of hydroxide because of the same problem that we just had. The same problem that we just had is, even on the surface of the iron oxide, if we end it without doing anything, then there are some bonds left over that can bond internally, but they generate a lot of strain, and so that surface is going to be super reactive. So if we have a super reactive surface, that's not going to last in the contact with the environment because there's all kinds of stuff that can interact with it. Let's just start with the water. So the oxygen has caused the oxidation, and the water can do something, and that can do something very useful. It can cap the ends of the bonds, which is very similar to what we were doing before. We find something that will sort of finish the bonds, and hydrogen is a good thing because if we have an OH, it only has one way in. So if we have OH as a functional group on the end of our metal, there's only one bond on the way in, so we can use up leftover bonds, leftover electrons. So this very surface is often covered with hydroxide just to, or not just to, but because that caps the oxygen free extra bonds. The dangling bonds are then not there, and so the energy of the surface is lower, and so we don't have it so reactive, and then it can stop doing stuff. Because this is a dynamic process, the iron oxide will grow until it gets thick enough so that the resistivity of this stack is high enough that it can resist the voltage of the iron and the voltage of the oxygen trying to attack each other. Oh, what about the fatty acids? So if we have a metal, let's have an iron. If we have a metal 3 plus and a fatty acid, they are going to interact with each other in all kinds of ways. So let's have that over there. So that will be our fatty acid can form a bond onto here. Let's do it like that. So I've deprotonated my fatty acid. Fatty acids are very common in the air because they come from us, they come from our fingerprints, they come from oranges, they come from bacteria. Everything makes them, living things make a lot of fatty acids, and they will attach via 2 bonds to a metal ion. They're chelating, they're coordinating to the metal ion, so they will often be found somewhere on the surface of our metal. The other extreme, iron is one extreme because it has a lot of things between the iron, metal and the outside. Even though it still looks shiny, it doesn't look very much different to any other metals, slightly duller. But it's got that complicated layer structure inside it that right near the surface. It's hard to investigate because if we scratch it to have a look, if we want to take a cross section of that layer structure, it will instantly oxidize up on that face. But what about this other metal? Oops, I've made myself all white, sorry about that. This other metal, that's platinum. Platinum is a noble metal that we find quite often in some applications. And if we have platinum, then it is a noble metal, so it does nothing at its surface. So if we have our platinum atoms at the surface, PT, they are perfectly happy without an oxide layer and without anything on there. Or are they? This is the platinum, for example, of my ring, and we have platinum metal atoms and the outside world, and they're just interacting with each other freely. There's nothing on the surface. However, what do we also know? We also know that inside vehicles is a catalytic converter. Inside the car, there's a platinum catalyst which is to oxidize carbon monoxide and leftover hydrocarbons up to water, carbon dioxide, so that they don't get released by your vehicle. And so we have platinum here that's not doing anything, and we have the other case where platinum does a lot. And so we need to explain that. And one of the ways that we can explain that, sorry, I keep looking at the wrong screen. One of the ways we can explain that is that these atoms that are on a step corner, for example, so if we make an island on this by growing half a layer, then there's a special atom here which is particularly unhappy. It's got extra bonds, it's got one extra bond that the other ones don't have. This one has 3 bonds to it, this one only has 2. And so even if we rearrange the surface to use up some of the extra dangling bonds, this one has still got more unhappiness. And particularly if it is a corner in 2 directions. So if we look at, try to draw it in 3 dimensions, so this is our island. If we have this one on the corner of our island, then in the other dimension, it's also got a problem because it's a corner in 2 directions. And so this atom here is particularly reactive. The goal of making a catalyst is to try to make as many of these as possible, or as many of the sites where the thing that we want to react will attach. So in this case, it will attach maybe along this. It will attach along this side of the island, and it will be able to bond and react. Going back to the surface of my ring, for example, if we take a piece of platinum that is relatively perfect, it's still going to have steps and edges on it because we don't have a single crystal with no defects in it. If we have that, then we can still make it less reactive, so it even though it's platinum and even though it doesn't react continuously, it can still be capped by, for example, let's have some chloride ions on there. So it can absorb some chloride or hydrogens, put hydrogen on there, for example, or maybe chloride, hydrogens, maybe oxygen. So it can absorb different elements, react with them to close off the surface extra bonds to make it even less reactive. And because that isn't going anywhere, it's just the surface, it will stop and not do any more reaction. So even on a surface such as platinum, we might see not platinum as the outside atom. And so to go back to our technical surface, here we've got our iron or steel. On the top of the iron we've got layers of oxides, and then on the very top of that we've got water and oils and all kinds of gunk that came from the atmosphere. So if we take this sample, for example, and we want to do something, paint it maybe we want to deposit some zinc on it, electrodeposit zinc on it, then we have to bear in mind that we have all of this to get through first, because we don't want to put the zinc on the top of here. We want to put the zinc on the top of here. The question is, do we take all of these oxides off first? How are we going to do that? How do we get these off? Where are they going to go? What are they going to react with? If we just dip our iron into molten zinc, is it going to explode? What's going to happen? What is going to react with what? So in that case, the zinc is more oxidizing than iron. So it will steal all of the oxygen off the iron, and it is hot. So it will boil all of this water off and probably the oils, although the carbon might well be trapped. And then we will get a zinc to iron, probably a zinc to iron connection, although there might be zinc oxide trapped in between, as long as we sacrifice some of our zinc as oxide to strip off this. But if we want to do it cold, so if we're doing it electrochemically, we then have a new problem, because it's not necessarily easy to do that. Or if we want to paint it, then we might have a problem with some of the other parts. If we want to put on a polymer, or we want to have a reflective coating, these things on the top may be a problem, because we might not be able to get rid of them. If it is a polymer, or we want to put on a polymer, we're limited to the harshness of the treatment that we can use, so we can't heat it up. Iron we can just heat up to 1000 degrees. That's going to solve that problem. Iron is not too hard to reduce back to the metal, so if we put hydrogen in, we can reduce it back to the metal. But aluminium, not so easy. Titanium, even harder. Silicon, very difficult. So it depends what the metal is and what these layers are, but very often technically we have to deal with them. With a coating process, we are going to have to play with these. Any glue that we might want to use to stick things together, okay, this is a nail, so it's a bad example, but any glue that we want to use to stick pieces of iron, pieces of aluminium together, will have to fight all of these layers. Any solder, any brazing process that we will do also interacts with all of these things that are on the surface in between the metal and the outside, because we want to get a metal to metal bond. Okay, that will do for today. See you next time.